Welcome to my presentation. I'm talking about learning-based design and control.
A little louder, please.
I will talk about learning-based design and control. And in this work, we optimize the parallelistic knee joint for quadrupedal robot animal and deployed it in various terrains, in the mountains, in the forest, on slippery ground, on cluttered ground, and various types of terrains, stairs. And this method works very robustly, so the robot didn't really fall at any time, and also was able to reject all types of different disturbances, as you can see in this part of the video. And also our mechanism was able to increase the overall operation time of the robot by 5% until the battery ran out. And the way we designed the parallelistic knee was by adding to the tie a linear spring and attaching an ellipse shape to the knee of the robot and combining them by a wire. And this way, optimizing it for actuator losses, we were able to reduce the actuator loss at 1 meter per second forward walking by 33%. And compliance in electric robots was already used quite a lot. For example, for the Enlo robot on top left for zero elastic actuators, as well as the Cassie robot. Also, parallel elastic actuators was looked into in the Asante robot on the top right, and IQ had linear elastic feet. And it's well known for compliance in electric robots that the robot gets more efficient and is able to carry more payload, which we are interested in as well in this work. The way how we accomplish our design optimization is by first using model-free reinforcement learning, where we would like to train one agent that is capable of controlling various types of stiffnesses. For example, on the left, high stiffness, medium stiffness, and no stiffness. And what we use is we take the teacher-student approach paradigm from the literature, and the agent is able to observe the full state of the robot in simulation. And the important key is here that the robot at any time observes the exact design parameters it is trying to control. And this way we get a design conditioned feature policy. And then we use the trained version of this one in our design optimization loop. Basically, we roll out trajectories in the environment with this feature policy and measure its performance in terms of, for example, actuator loss, and feed this into a Bayesian optimization, which then predicts or samples new design parameters, which then I can feed into the agent. And this way we try to find the best design given our objective function method. So this way we can optimize our design for various types of tasks. For example, standing on the left, carrying 20 kilograms, walking on various types of stairs, or flat terrain or rough terrain. And since I love to hack, I thought, let's actually build this on rough terrain, so we can take this robots in mountains. And this is the results that I showed you at the beginning before. Now, the question is, let's take a step back, think about linear systems. Here you have a simple two-mass oscillator in its equilibrium position. And as we all know, there are linear oscillations that are self-sustaining, so there are no actuator involved in this. And as long as I don't perturb it, this will go like this forever. So if we collect all of these linear oscillations, we get something called the eigenspace. Basically, whenever you are in the state space of the eigenspace of this system, it will forever oscillate if not perturbed. Now it turns out for nonlinear system, and the same set of periodic oscillations that we can also use. And here, for example, what you've already seen in Ian's presentation, this double pendulum has one of these so-called eigenmodes. And if we again collect the family of these oscillations, we get the so-called eigenmanifold. In this case, it's not a flat hyperplane anymore, but it is a bent curve, which is non-intersecting and time invariant. Now, we can show those efficient oscillations on complicated systems like the but it's still an open question, how should we transfer this to efficient motion on quadrupedal robots in terms of symptom gap, contact dynamics, and non-linearities in the real system. And for the future, I would like to continue trying to find these self-sustained oscillations in naked robots and exploiting natural dynamics. Also, I'm interested in exploring new morphologies. So here, for example, you see different types of number of links, link length, etc. So here we can just similarly apply our design optimization loop, or, for example, the PA is an example of advanced adaptation methods. And with this, I would like to thank you for your attention, and I'm open for questions. Yes.
I have the same question. Just why could you not take your simulator, put, say, a spring in parallel in series with every actuator, and take all those spring constants as design parameters and just optimize your controller? And then it's using the springs as well or better than what you're going to do.
Yes, I mean, I'm optimizing the controller as well.
No, but if you optimize the controller and the springs, and forget your core idea about nonlinear oscillators. Just what?
No. I mean, my approach doesn't take anything about the eigenmodes into account.
So you do optimize the spring constants as if they're controller parameters.
Yeah. So my controller just tries to find something that works as good as possible, given a set of design parameters.
And the spring constants are design parameters.
Sorry. The design parameters are those ones here. And you can think about, so this is quite simple, I would say. So this, maybe you could do optimization phase. The design space is not too big. But if you, for example, go to on the top right, if you have different types of links, different types of joints, maybe different actuators, all of this will get very computationally expensive. And the idea with this, training one teacher agent which is capable to control the robot in its whole range of design parameters, makes it much more efficient. So you can think about, if I want to take one robot and try to optimize the control, this will probably already take quite some time. And then I have one sample. And then if I do the design optimization, I take the second sample. And depending on the design space, this way will be very quickly very costly. So this way, I try to combine information from different types of morphologies in order for the robot to faster optimize the controller, such that I can have a controller and a design that work as good as possible together. Yeah.
Have you ever computed and compared the energy consumption in terms of like three stiffness setup, like higher stiffness, low stiffness? The energy consumption.
You mean for different spring parameters?
Yeah.
So the range is between super bad. So some spring parameters will just make your whole system really, really poor. And the best one is, for example, able to reduce the actuator loss by 33% compared to the robot without parallelistic actuators.
Okay.
But this is constrained by the system that we have. So for example, So if you remember the video on the bottom left, we saw animal robots really going faster. Actually, it was 8 meters per second. But for this, you have to change the actuators, the transmission. So actually it's unbounded. So theoretically, as you saw in the previous presentation, it could go to 0, the energy consumption. But yeah, it highly depends on your system. So if you cannot change, for example, the actuator, then you're very constrained by the maximum velocity of the joints.
So if you look at all the tasks that you had, the cams that you had there seem very different. How different is the performance between them? If you pick one, is it very suboptimal for the other tasks, or do they more or less all help, but one does more?
So they were all in range of 10%. So between 20 to 30% increase depending on what you're doing. For example, for the stairs, and all of this was optimized for 1 meter per second forward walking, except the standing one. So on stairs it was 22%, for example.
I guess more, is it a difference of how much they help, or does helping one help hurt other tasks?
For this one, I didn't experience that. For example, the rough terrain was also able to be better at the stairs terrain, but worse than the optimal for the stairs.
We have to get going.